So let's talk about nonlinear solvers. Gurobi has a lot of capabilities here, and we're going to cover them all in this presentation. We'll first talk about applications for nonlinear solvers, because some of you probably aren't using those functionalities yet. We'll talk about the quadratic solvers in Gurobi, the nonlinear APIs in Gurobi, more general nonlinear than just quadratic. And then we'll dive into the new mixed integer nonlinear solver in Gurobi. And we'll have a little walkthrough that really kind of demonstrates what Gurobi's doing when it's reading your model with these nonlinear functions. So let's get started. So there are currently 4 Gurobi model types that you might call nonlinear. And I guess it depends on how you count them. Maybe we could count 8, I don't know. It doesn't matter though. There's a group of solvers that are quadratic. We'll talk about those. There are higher order nonlinear terms than quadratic, of course. So we have a piecewise linear functionality in Gurobi that can handle those. And we have the new MINLP solver, mixed integer nonlinear program solver. And then there's also a capability of doing nested quadratics to handle that too. We'll talk about all that, but these are the kinds of capabilities in Gurobi that will be covered in this presentation. Okay, so why use nonlinear? The world is nonlinear. This is the first and the broadest reason I can give you. But there are physical laws, you know, in energy systems and other kinds of applications that you want to represent. And so a true nonlinear solver can help there. There's statistical measures in finance that are nonlinear. And there are nonlinear regressions that are sometimes applied in data science. And so there's a natural need for this. And of course, a lot of people are using linear approximations to replace that for performance reasons, because just to be clear, nonlinear problems are harder to solve. No matter how we construct them, they're going to be a bit slower than a linear problem, at least a bit, usually more than just a little bit. So in finance, we see this equation, y equals x to the 3 halves. It's something used in programmed trading applications. It measures market impact. And you can look at the literature on this, but the point is people writing these models for this kind of application, they don't want to use an approximation. They're very adamant about representing it as a true nonlinear function. So this is a great example of where nonlinear is needed. There are other kinds of nonlinear terms that are used in portfolio optimization as well. Those tend to be replaced by linear approximations, but perhaps now with a really fast nonlinear solver, you'll be able to do that in its pure form. In utilities, there's an AC optimal power flow model that most modeling of power grids is done with DC because it's linear. It's easier to represent in a math programming model, but it's more precise to do it with these nonlinear terms that they prefer. And so that's now possible with Gurobi. In oil and gas, that industry is full of nonlinear terms. I'm not a specialist in that area, but I know enough, I've seen enough to know that it's just full of nonlinear terms. A lot of models need to be representing nonlinear functions, and it's really necessary sometimes to do it in the pure form and not an approximation. And I have an example here of a heat exchanger equation that's used in some kinds of oil and gas processing plants. In engineering, the designs sometimes must ensure physical properties that are nonlinear. And so engineering design is an area where we see nonlinear applied a lot. And in agriculture, crop planning and management is an area where nonlinear terms arise. And that is another place where maybe now Gurobi can help with its new nonlinear solver. There are going to be more. I've talked to people about supply chain applications where a nonlinear term was useful in a particular application. So one of the purposes of this presentation is to get familiar Gurobi users thinking about nonlinear terms. Maybe there are nonlinear terms in your world that could be better represented in their pure form rather than as a linear approximation. So now that you have the solver, we're hoping that you'll use it and feedback to us how it's going. We'd really like to hear what applications are being created using Gurobi's new nonlinear solver. But of course, nonlinear, it doesn't mean just general nonlinear. We're also including quadratic solvers. So it's worth taking a moment here to talk about all of the solvers in Gurobi that are nonlinear. And so all of the ones in blue here are nonlinear. So all the quadratic solvers are 4 we're counting here, quadratically constrained, and then the MIP equivalents of those two. And then the non-convex mixed integer quadratic problems are also nonlinear. And of course, the new MINLP solver is nonlinear. So all of these count as nonlinear. Let's talk about the quadratic ones first. So these are all the different solvers that Gurobi has. And the one point that's important to make here is these are extremely performant. I still talk to customers all the time who have linearized some sort of quadratic term for performance reasons. And they discovered the need to do that maybe 5 or 10 years ago, and they're in the habit of doing that. There's no need to do that, or rarely is there a need to do that, because these solvers have gotten so fast. If you go back through our performance improvements over the last few releases, you'll see, and I've forgotten the exact numbers, but the MIQP and MIQCP have jumped like 5x, 7x, multiple times, so that these are so much faster than they were even 5 years ago. It's just really, I want to stress that so that you'll think about looking at it again. Nonlinear, rather quadratic problems are really tractable now with Gurobi. And so if you've been shy about using those terms, maybe it's time to experiment with them again. And our new non-convex quadratic solver, similar story, but more dramatic. It was introduced in version 9, I believe, and became faster and faster with each release. And it's like more than 80 times faster now. So it's really a mainstream capability of Gurobi rather than a new something unusual. It's really something to consider again if you had performance issues 4 or 5 years ago. And then, of course, you need to confirm you really need nonlinear because it is going to be slower than a linear equivalent. So sometimes, you need to measure the business value of the true nonlinear term. So you can usually do that with a math programming model. If I use an approximation and I can study how much deviation it might have from the actual nonlinear representation, is that deviation worth it for the solve time being a little longer? And so if it is, then you'll need to examine different ways to approximate, which I'll touch on in the next slide. And so another thing to think about now with machine learning, we see sometimes people trying to model predictions as nonlinear terms. Machine learning prediction will frequently be represented with some nonlinear regression of some kind. And that we can do for you. It's an automatic thing that Gurobi can do using Gurobi Pi machine learning. So it's not necessary to come up with a nonlinear formula and plug it in. You can actually plug in a machine learning predictor. And that's out of scope for this presentation, but it's a capability that's worth reminding you of here. So sometimes you can overcome this if you want to avoid general nonlinear terms like x to the 3. You can overcome it by nesting quadratic terms to replace it. And so if you want to avoid pure nonlinear terms for performance reasons, this might help. And then the multivariate monomial terms can also be done in the same manner, just having one constraint, and maybe, let's say we're trying to optimize, no, I say that's a constraint. So we want to have that constraint. We'll have 2 instead. We'll have x times y equals w, introducing this variable w, and then w times z equals d. So we'll have 2 constraints instead of 1, and that'll achieve the same thing mathematically. But now let's assume now you've decided you're going to do nonlinear and you want to use Gurobi to do it. So let's talk about how that's done in Gurobi. The API for doing this is actually 4 versions old. because we've had a capability in Gurobi for doing piecewise linear approximations with Gurobi on nonlinear terms. So we've had the ability to express these terms with our APIs, and I'm going to show you those now in detail. But just to give you a little landscape for where they live in the Gurobi API, there's a concept or a thing called general constraints in the Gurobi API. General constraints apply to a lot of different things, but some of them are fairly simple, like min and max and or and norm. These are, pretty simple APIs and really kind of distinct from what we're going to talk about now. The function constraints depicted on the right, we call them function constraints or automatic functions, sometimes we call them, are more complex, and that's what we're going to talk about for doing nonlinear programming. There are two ways that Gurobi handles these, as you'll see throughout this presentation, and one is to create a piecewise linear approximation, and the other is to solve it as a true nonlinear problem. So here are all the APIs we have. We have exponential functions, log functions, trigonometric functions, power function, and a polynomial. And so these apply to both piecewise linear and nonlinear. It's just a way to put a nonlinear function into your Gurobi model. These are the functions to use. And I'll show you a programming example of this towards the end. But the one thing to notice here, those are all univariate rather functions. All of these, they take one variable. And so how do we express something more complex like this? I can't, put in that full equation into Gurobi. So how do I express that? We break it down. We use auxiliary variables. Here we want to express this long function of x. And so we're going to use variables u, v, w, and z to decompose that. So we'll take the 1 plus x squared, and we'll assign that to u. And then we'll take u and say these are constraints, I should stress. So we're saying if you write a constraint that u is always equal to 1 plus x squared, we'll write another one that u is equal to v squared. That makes v equivalent to that square root term. And then we'll add w and set it to x plus v. That takes care of the inner term for this log function. And then so for the log, we'll set z equal to the log of w. And so then we can express the overall constraint above as v plus z less than or equal to 2. So we're decomposing it. And that's fine. Just a word of warning that as you get into this, it won't be a matter of directly writing out these long nonlinear equations into your model. It takes a little decomposition to do it. That's today. I can say we don't pre-announce features, so I can't promise this, but I would hope to see in the next release of Gurobi more accommodation for complex nonlinear functions, so that less of this will be needed with Gurobi 12. And part of the reason for that is that there is a word of warning on the decomposition. It's possible for the tolerance of the individual variables that we've added to be okay within the tolerances of the solver, but the original equation could be wrong and still be within tolerance because of this thing. Is if you look at the model at the top, y equals x over sine x, one solution comes out to that value. And so the Gurobi model for that would look like u equals sine x, v equals u to the minus 1, y equals x times v. And so here's one solution on the left here. Everything comes out just fine, matches the original arithmetic calculation. But if you look at the right, what if you have a deviation of some kind of 10 to the minus 6 in one of the variables? You can actually come up with a wrong answer for y when in fact all of the variables are within tolerance. So that's just a little minor word of warning. This is something that will be addressed, as I say, in the next release. So look for that, but just be aware that this is possible. Watch your tolerances. Okay. So now let's talk about specific solvers for using these functions. And so we have these automatic functions, or they're automatic piecewise linear functions that you can use as constraints. So let's imagine this blue curve on the right, and we're going to replace it with these red line segments. The real implementation is usually more than 3 segments, of course. We're trying to be more precise. And in fact, the solver gives you the ability to specify precision. How many line segments do we need to get them as close as we want them to the original curve? And you're able to express those precisions any way you want. For example, you can say, don't ever let it deviate by more than 10 to the minus 3 or whatever you want to express in there. The more precise it is, the more of these line segments will be generated. And so you're creating a harder problem to solve, or a larger problem, as you make things more precise. So beware of that. But it's there, and it's been in Gurobi since version 9. It's really quite a nice capability, because people used to have to do their own piecewise breakdown. And this is really elegant. It's a nice way to do a nonlinear problem without turning to a nonlinear solver. So this works, it lets the Gurobi solver work on a linear representation for faster solving usually, but it can generate a very large problem if it's generating a lot of line segments. So in fact, it could end up being slower than the MINLP solver in some cases. And speaking of the MINLP solver, we'll use those same APIs we just talked about, but we just have to give Gurobi this parameter in the right-hand side of the screen, func nonlinear equal 1. Just by telling the solver we want to use the true nonlinear solver, we'll start solving it in a different way, not using, and the solver won't generate any piecewise linear terms. So it's solving global optimum for that nonlinear function, or however many you have, and it's not using an approximation in the way that the piecewise linear terms are doing. So you're getting an exact representation of the problem that Gurobi solves. And that means also means a smaller problem size, as you'll see. I'll show you that in the demonstration. But the process of doing it is using branching, which I'm going to show you now, and that takes time. So in order to make your best decision about this, it's kind of nice to know what's going on under the covers. As with most Gurobi algorithms, it's possible to use it without understanding this, but it's good to know what's going on. So it uses a branching mechanism, much like we use in mixed integer programming. So just a quick review, when you're doing an integer program, you encounter a fractional value. Let's say you have for x a solution with value 3.5, and let's say x is an integer. So now you're going to branch on that. You're going to say, okay, let's look at all solutions where x is 3 and all solutions where x is 4. And then because you can't have a fractional value for an integer variable, and that creates this tree of branches and nodes where you're solving linear relaxations over and over again, but testing it by setting x to one or another integer value. And that's how branch and bound works in integer programming. We're doing kind of a similar idea here. The branching is really exactly the same, but we're branching on a different criterion. Here we have this blue curve, nonlinear term of some kind. We'll draw 3 lines to describe this one, however many lines we need. Sometimes it's 4. But this one, we're drawing a line through the two, the lower bound and upper bound of this variable x. There's a black dot under my mouse pointer here and one here. Those are the lower and upper bounds. So we just draw a line through those. Then we draw a tangent line at those points to the curve and create 2 more lines and then a solution space. You can see it's pretty loose around that blue curve. It's not very precise. So we'll go through this process. We'll say if lines are within tolerance. If this distance from the red lines to the blue line is under tolerance for the solver, I think it's 10 to the minus 6. Wouldn't swear to it. I should know that, but I don't. But it's a small value. Let's say it's not there yet. It looks like maybe in this chart it's not. Then if it's not, we'll split the curve into two pieces and try again. We'll just go through the whole process again. If it is within tolerance, we're done. Because we're trying to solve, as always, to a certain tolerance level. So this way we're able to use kind of linear practices. It's still called a linear relaxation, these red lines are. And we're just solving a linear problem then once we're within tolerance. So let's look at the case where we split this because it's not tight enough. So we've decided now we're going to branch, and we're branching on this value of x, whatever that happens to be. We'll call it branch value. So if x is greater than or equal to branch value, we have this curve here, and we'll draw two new tangents and, and an intersection line for those. We've moved that lower bound up to our branch value. The lower bound is a branch value in subproblem 1. And in subproblem 2, the upper bound is now the branch value. So we're doing this, breaking it down. It looks like maybe, I don't know, in this representation, it looks like from subproblem 1 might be within tolerances. So we'll stop for that one, but it looks like subproblem 2 still needs another branch. So more branching would be needed. This is the concept to keep in mind while you're thinking about what the MINLP solver is doing. And you could imagine with more complex curves, the branching could get pretty involved. It could be a lot of branching. So if you look at that sine wave in the bottom, we have a lot of space that's nowhere near the curve. So we're going to have to start branching like crazy there. Who knows how many branches we'll have. And so, but just specifying func nonlinear equal 1, you're asking Gurobi to do this instead of using the piecewise terms. And the upshot of all this, actually, if there's anything I can ask you to leave with from this presentation is to remember this. The bounds and the variables are critical for this. If you look at this chart and we have a lower bound over here on the far left and an upper bound on the far right, you can see there's a lot more branching going to be needed. We have this whole space between L and L prime that'll have to be branched on. Whereas if our lower bound were L prime, we could avoid doing all that branching. So every little effort you can make at tightening the bounds of your variables will make this problem solve much, much faster, not just a little bit. Bounds are critical for MINLP. So now we'll do a bit of a walkthrough. We have this model here. I've expressed it on the right in mathematical terms. Sine x plus cosine 2x is going to be minimized subject to these two constraints. Okay, not a terribly complex function, but you can imagine the same thing would apply with a more complex nonlinear function as well. So we'll just add the variables. We're adding also auxiliary variables to describe to make it univariate, to break down these functions so that we can express them with the Gurobi general constraints. So we're creating a variable 2x to take care of the 2 times x function, cosine 2x to take care of that whole latter part of the objective function. We have a sine x variable to take care of the first part of the objective. And then we have exponent x to take care of the e to the x bit in this constraint. We'll set the objective to the variable named sine x and cosine 2x, minimize that. And then we'll start adding constraints, and they're expressed, some of them just in linear terms, but the last 3 are using our general constraints. So this is what the general constraints look like. We have a sine constraint. We're saying, give me the sine value of x and assign it to the variable I've created called sine x. We're not saying that actually, it's a constraint. So we're specifying it in the solution that x will always be equal to, or rather sine of x will always be equal to the sine of the x variable. And then we're calling that general constraint 1. Then we do the same for the cosine 2x variable. passing the general constraint cosine, the variable 2x, and saying the cosine value of it should be in this variable cosine 2x, and so on. So we're breaking down the problem as I described in the previous slide. And when we solve that, well, in order to solve that first, we're going to solve it two different ways. We'll set func nonlinear equal to 0, which that's the default. We don't have to specify that at all, but that's currently the default for Gurobi. And that means that it will generate piecewise linear terms. So I'm writing the model to automatic PWL, and that way I can look at all these piecewise terms if I want to. And then I'm optimizing and printing the solution. The second time I'll solve with func nonlinear equal to 1 and do similar steps to print the solution. So let's look at those. The output, first of all, is kind of interesting. We can see for the automatic piecewise linear solution, Gurobi pre-solve added 40 rows and 117 columns. And that's kind of one of the key takeaways here. It's generating a bunch of terms in the model that Gurobi is then going to solve in the usual way. These are all linear terms that it's generating, and I'll show you that. Using the MINLP solver, we've set the parameter func nonlinear to 1, and so the pre-solve's not adding any rows and columns. It's just solving the problem. And I'll be able to show you that in just a second. You can see the objectives are within tolerances the same, and it's just simple to use. You just tell it func nonlinear 1, you get the MINLP solver. Very simple. Okay, so the LP files that are generated are actually pretty much the same because it's not showing what the pre-solve is doing. So to get a look at that, and this might be useful in other things you do, you can actually look at the pre-solved model instead. So if we tell Gurobi to pre-solve the model with this model.presolve function, and this is available, by the way, in all the APIs, everything I've talked about is available in every language Gurobi supports. I'm showing you Python because it's the most common language people use and fairly easy to understand. But we can save that pre-solved model to our own variable and then write it to an LP file, and then we can look at it. And it's pretty cool. I'm going to show you that now. But when we compare these, the thing to look at is the piecewise terms are going to be linear, and that makes them faster to solve. But the piecewise model is going to be bigger. It might make the MINLP faster to solve. So let's look at that now. So on the left, I know this is very small type, but it'll still get the point across, I believe. On the left, we have the piecewise linear version of the model. We can see the actual function here for the objective function. But on the left, we have all of these piecewise terms, and the one thing to notice is they're all linear. They're just regular linear expressions, and it goes on and on and on, lots of them. On the right, we have a 36-line file. And so we have the objective function expressed as a nonlinear function. We have some constraints. Those are all building up from the code that I'd written, just direct consequences of that code, but and bounds. But notice that some of the constraints contain these nonlinear terms, or nonlinear, how did I express that? The variables that contain the nonlinear terms. So we have a fairly complex objective function that's nonlinear, and we have some nonlinear terms here. Let's see. And so that you're getting a true nonlinear representation of the problem. That's what I'm trying to say. And it's smaller, much smaller file than the piecewise linear expressions on the left. So that means that sometimes MINLP solver is going to be faster. No, not always, and especially in this first version, I think it's good to experiment and see which one is going to be faster. But as time progresses, we can take heart from the past experience we've had in the non-convex MIQCP solver that Gurobi released in version 9. And we could see that the performance improved radically there. I would expect to see a similar kind of I don't know if it'll be this much, but some radical speed improvements in this function and in the nonlinear functionality in Gurobi in coming releases. So usually we work on numerical stability first and then begin to work on speed improvements from there. And so you'll see radical improvements from the MINLP solver in Gurobi in versions 12, 13, and beyond. But it's really good to start experimenting now because sometimes MINLP will be faster than piecewise linear. But it's it's really a new time for Gurobi. This is a great capability that's been added. And if you're a Gurobi user and you have a license, you just inherit all of this capability with version 11 of Gurobi. And so we're really proud to offer this, and we hope that you'll use it. If you do, the most critical thing I can ask is to please share some of your models. We need them for testing and for performance testing, but also your experience with those models is critical to the improvement of this algorithm. We have the dev team really eager to see your models and to help work on the performance of individual models. That's where a lot of these improvements will come from. So that's the presentation. It went fairly quickly, but we have time for questions for sure. Do we have any questions?
Yes, we have many.
Good.
Let's see. Well, an easy one. Do you know if this functionality is also available in MATLAB? Because a MATLAB user is worried that many functions are only available through Gurobi Pi, or well, like some convenience functions are available only through Gurobi Pi.
I don't believe, well, actually, I don't know. I assume it's not yet available in MATLAB. Do you know if it is, Juan Antonio?
No, I'm not sure. That's why we left it open.
I don't believe it is because they would have to write interfaces to support that.
Yeah, we have a code example on using func nonlinear. We have an M file, so a MATLAB file.
Oh, we do.
Yeah.
Oh, excellent. So then it is.
I think another person asked this question, so you could probably find it, including the link in the list of answered questions.
So we have it in the product, the func nonlinear example.
Yes.
Let me just show that. So he's referring to the MATLAB examples that come with Gurobi. If you go to your Gurobi installation, I'm going to mine and sharing it here on the screen. Can you see my screen?
Yeah.
Okay, good.
Go to MATLAB.
So under examples, there is a MATLAB folder.
Then func nonlinear.
And there it is right there, func nonlinear. So the answer is yes. Fantastic.
Cool.
We have another question that asks about callbacks. So if callbacks are handled any differently when using func nonlinear equals 1, for example, if a solution is found when solving a convex MINLP, if users can still add cuts or inject solutions.
I would expect they can. I don't see a reason. No, I would have fully expected I haven't done it, but I would expect that capability to be fully functional.
I agree. So I checked the callback codes and you can still wait for a MIP solution to be found. And if that's the case, then you should be able to inject solutions and add cuts, just like when solving MILPs.
Great. Any other questions?
Yes. Arjams asks, was there any investigation comparison versus K-Nitro or other MIMLP solvers?
Well, we don't publish internal investigations. I don't know of a third-party test that's been done yet. Do you, Juan Antonio, do you know of any third-party benchmarks?
Not that I'm aware of.
Yeah, certainly. I'm sure the Gurobi dev team has done that, but I don't. Well, I'm not even privy to those kind of internal tests because, of course, you have to question the meaning of it coming from a vendor. So we don't usually do that. We don't usually publish comparisons with other solvers that we've done. If it's third party, yeah, but otherwise we don't publish them. Any other questions?
There's one question about nonlinearity functionality available with Pyomo. So I guess this is about being able to use general constraints in third-party interfaces. I'm not sure, and maybe you can add some of that.
It might be possible. We'd have to. So I've just had second thoughts on my first comment about MATLAB. Because these APIs have been available since version 9 of Gurobi, many of the frameworks and third-party modeling tools will support them. And all you have to do, if they do support them, they were doing it originally for piecewise linear terms, but they'll also be able to, Gurobi will also be able to solve it as nonlinear because it's parameter based. We haven't changed the Gurobi API. We've only added a parameter. So there's a real good chance that Pyomo would support that. And all you have to do is first of all, try the APIs and see if they work. It'll be the Pyomo APIs for nonlinear terms. See if they're generating piecewise linear in the Gurobi model. You can do that by writing the Gurobi model to disk and just see what you get as an LP file format, for example. But then if you want to solve it as a nonlinear, just set func nonlinear, the parameter, to 1, and it should work. I'll be interested to hear. I haven't done it with Pyomo. I'll be interested to hear if it works. But now that I think about it again, I think I would expect it to work. It's been 4 years now with nonlinear functionality in Gurobi.
Yeah, maybe to add a general remark about third-party frameworks is that in the end, it's up to them, right, to include solver features into their framework and interface. So sometimes it might be available directly. In other cases, it can also be possible to interact with the solver object through a third-party interface like Pyomo. So it might not be listed as a Pyomo functionality, but by directly interacting with the Gurobi solver object through Pyomo, you might be able to then use general constraints.
Thanks for adding that. Yeah, that's a good thing to point out. Thank you.
There's a few questions about like solve time and complexity and comparing like linear formulations with nonlinear formulations. So maybe then you could maybe give a rough answer to many of these questions about weighing of the trade-offs between the two.
Yeah, it's let's see, where do I go for a slide on this? I think of this chart when I'm thinking about that. Mostly you're going to get a faster solution from piecewise linear approximations today. I'm told by the Gurobi dev team who created this that we should expect that to change quite a bit, maybe even radically over time. Even today, though, because the model size is smaller, sometimes the nonlinear problem will solve faster than the piecewise nonlinear. Usually for smaller, like where the expression is not too complex or there aren't too many nonlinear terms in the model, then you'll get a faster solution from MINLP because it's a smaller problem and less for the solver to do. But that'll be a very minority of cases right now. The majority will be solving faster with piecewise linear approximations. But as time progresses, and the next release will be version 12 of Gurobi, and the versions after that, as time progresses, that's going to change. And so really the developers are eager for the users to be sort of aware of this and experiment as time passes with their particular modeling needs, see if their model solves better with nonlinear. Over time, it likely will solve better as a nonlinear problem. But there's no way to predict it, except model size maybe. I mean, if you have a lot of nonlinear terms, it's more likely that the piecewise solver is going to win today. That's the only generalization we can give. There's no way to quantify it because, of course, each mathematical, each of those univariate expressions that we allow, each of the APIs varies in its performance. So the kind of nonlinear term you're trying to model will have an effect on performance as well. So we can't really predict which, we can't give you criteria to predict which solver is going to win. But more importantly, it's going to change over time. So we would encourage you, kind of beg you to please try it with each release. It's a little bit of work, but you may get performance benefits out of it. And we would sure like to hear about how you're doing with that, if you can share that with us. Would you add anything to that?
No, I think that's a good description, yeah.
Okay.
We have another question from Marion. They are curious about the difference between having nonlinear terms in the objective function as opposed to the constraints. So maybe it's the question of whether it works and also how this might influence.
It works. Let's see. Wait, no. We were offering, no, you can't have nonlinear terms in the objective function itself. We're offering, we provide nonlinear constraint APIs only. So you can't put the nonlinear terms directly in the objective function. You have to assign them to variables and put those into the objective function. So our APIs only support nonlinear constraints.
Yes, so I guess the objective function can be quadratic, for example, and of course contain like.
I'm forgetting quadratic. Thank you.
Yeah.
Except for quadratic. Thank you.
Okay. There's also another interesting question about how IIS handles nonlinear models, whether things like an LP file can be created. Or like an IIS.
I haven't experimented with IIS and nonlinear. Have either of you done that?
I've not done it yet. I'm not sure about Tuan. If you got this question before.
That one.
Which question? I'm replying to.
Yes. So this is about creating IISs while solving nonlinear models. If you can still have like if you can export an ILP file the same way.
I'm not sure. I mean, the issue is that when we're trying to use several Gurobi features at the same time, it is not always the case that you can use them in combination. I haven't tested that myself, so
we'll have to get back to you with an answer on that. Yeah, I guess that's the best approach. Can we do that? We'll get back to you with an answer on that. But like, I'm thinking about. So I don't know about IIS. We'll have to find out and get back to you. But like for fees relax, there's no reason that shouldn't work. We're just introducing Slack variables there, and so you can use fees relax with nonlinear, I'm sure. IIS, don't know. We'll give you an answer by email. I mean, I'll do that. Are there any other questions?
Yeah, I'm still browsing through. There's a few like general questions, like one user has bilinear constraints, and it might take too long to use, like to test the MINLP feature. So he's asking about general suggestions on how to increase the speed for this bilinear constraint model. there's a few similar questions. So maybe Dan, if you can comment on like parameter tuning or solver performance in general.
Well, I mean, the first thing for nonlinear, of course, is to tighten the bounds of variables if you can. Look for ways to do that. Parameter tuning for nonlinear. So I guess I'm not following the question. Is it about mixing bilinear with nonlinear, or?
No, so currently they have a bilinear constraint, but they might not have the time to test the MINLP feature. So they're asking about general like recommendations for speed improvement. Yeah, so
Well,
I guess it holds. Yeah, go ahead.
The best thing to do is to submit your model in MPS format to Gurobi, and we can tune it for you. That's really a great capability that commercial users of Gurobi can all do, and we'll be glad to test your model and tune it for you. Tuning is quite a deep subject, and deep and broad both. I mean, there's a lot to know to do tuning. I mean, if you're an experienced user, many of you are doing this already, but the expertise required for the average Gurobi user, I think, is a little beyond the time you can put into it. Certainly you could learn it, but it would take too much time. So that's why we offer this tuning service. And I think that's the best answer I can give is let the Gurobi experts team tune your model, and they'll find the parameters for you. This I think is even more true when it comes to the bilinear solver, that it's a newer capability and probably harder to learn to tune that than other linear, other types of convex models. I think it's a good prospect for Gurobi experts tuning.
Thanks, Dan. There's now a question about Gurobi machine learning and whether it's compatible with MIQPs.
MIQP. I assume we're using quadratic terms in there. Gurobi's translating the predictor that's generated from, or the predictor that's passed to the Gurobi APIs through Gurobi Pi machine learning. It's doing a translation, and as part of that, it's using some of these APIs we talked about today. Whether it's using quadratics or not, I assume it is, because that's a capability that it wouldn't ignore. Anyway, I don't know that, though. I haven't looked at the internals of that, whether we're actually using quadratics or not. I would expect that we are, though. But it's also using nonlinear terms where necessary. So it's a nice, to me, a convenient black box that I haven't dug into. So well, actually, we can find out, though. I'll talk to Pierre, the developer of that capability, and I'll find an answer for you and email it to you.
Thanks, Dan. There's now a question about, so this is, I guess, about determinism, and the user would like to know if when running Gurobi multiple times on the same MINLP, if you would be getting different solutions or if the solution's always globally optimal.
Always globally optimal. Why would you let me think about the question.
Yeah, so I'm thinking this might be coming from like local solvers, right? Where depending on the starting conditions, the local solver might terminate in a local optimum.
No, this is because of the way we go about it. This is global optimum using the branching capability, but it takes time to do all that branching. That's the trade-off.
Yeah, and then
sorry. And it's another reason why I'm going to keep saying this to remind you to tighten your variable bounds. The tighter they are, the less solution space there is to explore and branch on. Sorry, Leonard, go ahead.
No, yeah, this was the second question on how like the bounds can affect solution time.
Just enormously, enormous effects. Even minor changes to the bounds probably will have significant improvements in performance.
There's now questions on whether the MINLP branching or in general the solver can be controlled with parameters or callbacks.
I haven't heard of callbacks. Well, to the extent that it's an integer problem, you can use the integer callbacks and the linear callbacks. I don't believe we have hooks for callbacks yet, at least in our callback API. In fact, I'm sure we don't yet. But something to watch for in the future. If you have a particular idea along that line, can you please submit it as well? The best would be if you could submit it as a support request, but get it to us any way you like, and that would be interesting for us to hear what you're interested in.
Thanks, Dan. Okay, let me quickly scan. So here's a question about the difference between solving NLPs and MINLPs. So all continuous, but still nonlinear versus some mixed, like integer or binary variables, I guess.
Well, the integer is easier. First of all, I'm not an expert. I don't have a lot of experience with NLP, general NLP solvers. But I can tell you that the integer aspect of this makes it much easier to solve because we can use cuts and we're not having to consider continuous variables as much, at least, and it makes the branching easier to do. You're not going to branch, for example, if X were an integer variable, you would branch somewhere that you're not having to consider the whole space between the integer. How am I describing this? You have fewer options to consider when you're branching when it's integer. Plus, you have the ability to do cuts that are reducing the solution space all the time. So it simplifies. It's easier for an integer problem. So if you have integer variables, it actually makes the nonlinear part of this easier to solve. That's a bit of a rambling answer. Did that answer the question?
I think so. Yeah.
There's an interesting question here, if I may. Ray Zimmerman asked, does the MINLP solver provide shadow prices on the nonlinear constraints?
I don't know. Do either of you know, Leonard or one? I don't know that. Would it? Let me think. We're doing a linear relaxation. Let's see. Let me think. Actually, I just don't know. I'll find out, and I want to know that, so I'll find out and provide an answer after the session.
Okay.
There's another question, and we had a similar question before, so maybe it makes sense to reiterate. So the question is whether Gurobi automatically transforms a nonlinear problem with a nonlinear objective function into a nonlinear problem with a linear objective function in nonlinear constraints. So I'm guessing this poses the idea to create an auxiliary variable, right? And whatever the term is you want in your objective function, you're then going to define it as a constraint. And we had a similar question before, I think.
But it's not automatic is the answer. If I understand the question right, the answer is no, we don't do it automatically. You have to express that in your model. You have to do that conversion yourself.
Yes. Thanks, Dan. So there's now a question about whether the MINLP solver can make good use of starting solutions.
Sure. I mean, because they're integer variables, you can give them, pass them values, and because there's a whole integer solve going on at the same time, that's a viable tool. Absolutely. Any other questions?
Yes, so there's one question again on the global optimality aspect. The user wonders if this is only guaranteed for mixed integer NLP, but not for NLP.
Well, you can pass a non-integer problem to our solver and it will solve it. So it's still guaranteed global. Because the branching is, remember the branching, there are two kinds of branching going on. In this discussion, I was talking only about the MINLP branching, but the integer branching is separate from that. It's still going on too. So don't let that confuse you. The MINLP branching is still going to do its job. It's just, if it's not an integer variable, it might be harder to find an answer, in fact, for MINLP, but it will find an answer and doesn't have to be, it can be a continuous model instead of integer.
Okay. Now, this is an interesting question, I guess. So the user wonders if there's an automatic way to get active constraints after resolution. So I guess once Gurobi terminated and you have a solution, which constraints are actively
Which ones are
constrained?
tight, you mean?
Yeah.
Yeah, so that's relating back to the shadow price, and I would expect that you could just do it as if it were a linear problem, but I need to test this. I haven't done this myself, so I want to see it for myself before I answer these questions about shadow costs and things like that. So I'll answer this one by email as well, because this is something I need to know. So I'll answer that after. Sorry, I can't answer it now.
There's also a question about the size of problems. So the question specifically about how large a non-linear or non-convex problem could be, but maybe it makes sense to comment on like generally, right? How large a model could be and how this affects Ruby usage.
So there's so many dimensions we could talk about. And first of all, I don't have rules of thumb here to share. That's what they're looking for. Is I think whoever asked that question, I think you're looking for like a rule of thumb. If you have, 10,000 nonlinear constraints, is that too large? And I just don't know, because first of all, it'll depend on those constraints, how complex they are, how interdependent they are. I just don't, so I haven't bothered. I'm sure someone here has, but I haven't bothered to do like experiments with different size problems to see which one, where the borderline is. The fact is, I don't know that answer. And even if I could learn the answer in version 11, it's going to change with version 12. And how long do we have? Just a few months. We'll have version 12 out. So not really worth the experiment on version 11 or even on 12. What we are asking is for you to please try it. And if you hit a wall and it's taking a very long time or not solving at all, please tell us. This is the kind of feedback we really value. And if you have a problem you really want to do nonlinear, getting us a copy of that problem now to help tune it for you, and also to so the developers can see it and work on the solver. We'll be actually tuning our solver as we go forward against your problems. And so if you have one that you want solved, really please submit it as an expert's ticket in our support system. And we'll not only tune it for you today, but there's a really high probability that will affect the direction of development on this solver going forward. So that's not answering your question, and I apologize for not having that kind of rule of thumb handy that you're asking for, but this is really a valuable thing. And if you have a problem that's worth worrying about, then letting us work on it will really benefit you, I think, in the long run. Did that answer the question, do you think? Was it Leonard or one?
I hope so. Otherwise, feel free to pose the question again in a similar or different format.
Dan, did you already commented about providing initial guesses or starting solutions?
Yes,
for the
yes. So
MINLP solver? Okay.
Yeah, especially for integer variables, that's always going to help because there is still this integer solve going on. So yeah, we did answer that though.
Okay, thanks.
Okay, here's another one. Okay, so let's say you have a term with a square root, right? So the square root of x is greater or equal than y plus z or something. And then you could reformulate that, of course, by squaring both sides, right? Then the square root is gone, but you have a square on the other side. The question is how Gurobi handles this in outer approximations, because a function like this might be not defined at x equals 0. But
That's a good question. I don't know the answer to that one. We do have a square root in this example. No, not in this example, a different one. This one. And so that's how you handle it in code, but what's Gurobi doing in the, I don't know. Leonard or Juan, do you know the answer to that? I just don't have an answer for that one.
I could imagine that it, sorry, one.
No, go ahead.
Yeah, I was just gonna say that I could imagine that it might be like a tricky area to branch on. But otherwise it's going to be considered, right, as part of so the feasibility tolerances will still be kept, and I don't think it matters if you input it in one way or the other.
Yeah, so I guess we're saying we have confidence in the dev team to have handled that correctly, but we don't know how they did it. Yeah, it would be quite an oversight because we are advertising global optimum here, so it's not something we would do lightly. It's something that's been considered. Any other
Okay, one
questions?
user asks if we could share the LP files with the
Sure.
recording, like the LP files that you showed. I'm not sure if we can make this available via the website, but maybe if people ask via
Well,
support.
actually, we can share them, but you could do your own, actually. Let's see. Let's get this code on the screen and you could take a screenshot of it. Find it. Here we go. Hear that. Sorry for the mess on my screen here. I'll fix that. So if you want to screenshot this, let me make sure I've got the right thing here. I've got the wrong thing here.
MATLAB. Okay.
Here. So starting here, if you want to screenshot that, then I'll scroll down. You can screenshot it again. You can generate your own and have a look at them. It's pretty simple code. And one more screenful, I think, will do it for us. So I'll wait a moment for this first half, screenshot it. And now I'll scroll down and you can screenshot again. And then you're done. It'll generate these pre-solved files for you. It might be it's a nice little exercise too. I think this is a really, we use this writing of the pre-solved model a lot in tuning, because it's really useful sometimes to see what's been generated by pre-solve. Sometimes you just wonder what's going on in there, and you don't have to treat it as a black box. You can pre-solve the model and write it. So it's a nice technique to know about too. So I'll stop sharing that code now, but those two screenshots will do it. But I'll look for a way to share. Oh, we'll put it in the, we'll make a PDF of the slides. Those will be made available after. I'll include the code here in that PDF. I'll make sure to do that too. Any other questions? This is great that we have a lot of questions because the presentation was quick. I'm glad we have a lot. We made our hour after all.
Yeah, so there's another question about your slide where you explain the outer approximation. So the user says that you used 3 segments to approximate a nonlinear curve. And then he asks, in case the nonlinear curve represents an inequality, do you use outer approximation?
If it represents an inequality, let me think that through. I don't see the inequality. I mean, these
Yeah.
lines are these lines could be an inequality or an, no, I mean, they are inequalities. We're saying the solution is greater or equal to, oh, I see. They're saying it in terms of the blue line. It's an inequality. Well, I mean, so this is I guess, an oversimplified example. What are we expressing here with the blue line? We've got it doesn't matter. You're still going to generate these lines. We're trying to generate some kind of linear representation of that curve, whether it's an equality or an inequality. It doesn't change the need to generate the linear approximations of that. I'm not sure I follow. So it would work, but the process is the same regardless of the sense of the constraint we're trying to describe.
Yeah, I agree. Okay, so then now there's a question on what happens if Gurobi cannot find a bound for the variable that it needs to branch on, if this is something that could happen. So this is for the auto approximation branching also.
We can't find the bound. It has the bounds, and they're there by default. It's 0 and infinity. I mean, so if there's no upper bound, I guess that's what they're asking. Yeah, we're winding up. We probably should make this the last question, but I'm going to need help. Leonard or Juan, I don't know the answer to this. What if it's unbounded? What if we have an upper bound of positive infinity? How do we handle that? Do you know? I don't know that.
I mean, you can always hope that pre-solve finds some variable bounds based on the other relationships. But I mean, it's always like a best practice to try to provide variable bounds that are as tight as possible, right? Because
the question is
if you
pretty
fail to do that,
legitimate. The question is pretty legitimate, and I'm wondering why I haven't asked it myself. What happens when there's positive infinity upper bound on that variable x in this example? We don't know what that curve. The curve could do any kind of crazy.
I mean, the McCormick envelopes will not be of high quality. So of course, it may take like longer to process to solve that problem. That's why you should always try to provide these variable bounds.
But you've given me food for thought, whoever asked that. I appreciate you asking. Yeah. It is interesting to think about. I know they're handling it because we're doing similar things as Juan Antonio just suggested with a non-convex quadratic solver. And so, but this is a different question. I'm going to try to answer your question by email. If we have that person's email address, I'll try to answer it by email. Because I need to research it. The point is, I don't know the answer. I'll research it myself with the dev team.
Okay. Thanks, Dan. We hope you enjoy the webinar. Thanks again, and we hope to see you in our next webinar.